Okay, so everything was in a line. Now there could be also cases when the variables or the solutions are cover more than a line, which could be a plane. Now we could go actually. I can provide an example here, and but for so the steps, we're not going to do all the steps in between, but just we have to cover it for a moment. So let's imagine that we have a system that looks like this: x plus y plus 3z plus w. This is equal to 2. X minus y plus z plus w. This is equal to 4. And y plus 2z plus 2w, this is equal to 0. So starting with this system, we can write this one as 3, 1, 2, and
1 minus 1, 1, 1, 4.
yes, 1 minus 1. So someone
0, 1, 2, 2, 0.
Okay, that's good. So we should start on here. I'd like someone among you to turn off the microphone because there is an echo, but it's gone. Okay, thank you. So we start with the system, and we know what these are. So this is the augmented matrix. If you follow all the steps that wait, let me see for a moment. No, actually, probably I will not select this case because this is a simple one. I might go with one case where the solution is more complex than this. So allow me to give you another. X plus Y plus Z plus W. I apologize, but let's assume that let me write it right here. Okay, so let's imagine that we have this system, and this is the augmented matrix. If this is the augmented matrix, it looks like the coefficient matrix A, it is 4 by 5, okay? Then, because that's what we observe, we have 4 equations, 4 rows, and 5 unknowns, and if we multiply this with a vector, which is 5 by 1, we get the vector B, which is 4 by 1. And these will be related by. So this is what we see from this system. And we have here 4 equations and 5 unknowns. Okay. Then, if we follow all the steps or all the procedures that we explained in the previous session, but in the end we are going to get. So let's write here the answer right away, without so we can skip all the repetitions when we obtain this. And I hope that that was. You have any question? Okay, so starting with the there's a question. Okay, see the problem we are facing. Okay, so if we look at this final reduced row echelon form, so this is what this is. This is the reduced row echelon form, and the leading ones are these. So in the first row, this is the leading one. In the second row, this is the leading one. In the third row, this is the leading one. So it looks like the leading terms, we have here x1, we have x2, and x4. The terms that are non-leading, we can denote them in blue, where actually
x3, x5.
that's the normal. And this one. So non-leading it is x3 and x5. If x3 and x5 are non-leading, we can write the following. We can say that x3 this is equal to s, and x5 this is equal to t. Okay, so they are free variables, and we can say that s and s is it belongs to the real number space, and t is the same. So they go from minus infinity to plus infinity, but including also the 0. So from these equations, what can we obtain? What can we write?
For the first one, we have x1 plus x5 equals 1.
Yes.
For the second one, we have x2 plus x3 equals minus 1. And for the last one, we have x4 equals 3.
x4
For the third one.
That's very nice. This was good. So it is obvious that from all this large volume of information, which is encoded in these equations, we can get a simpler version like here. Okay, but now let's not forget that x3 and x5, these are equal to s and t. Okay, so these lines in blue, let's not forget what they are, and let's write for a moment x1, x2, x3, x4, and x5, these variables, we can write this as a constant term, okay, plus s times another vector, plus t times another vector. So what is x1?
1 minus t.
1.
And 0 and minus 1.
Now, yes, x5, it is 0, sorry, x5, it is t. You know, maybe it's better if we do it like this. That's right here. From this expression, we can say x1 is equal to 1 minus x5, which is minus t, right? x2 is equal to minus 1 minus x3, which means minus s, okay? And x4 is equal to 3. So let's have a look at these equations here. It could be easier. So x1
0
minus 1.
minus 1.
x2
Minus 1, 0.
Yes.
3, 0, 0.
0.
For x4. What's that?
What about x3?
0, 0, 0.
0 1.
No, x3 is 3.
Yeah, exactly.
0,
1
1, 0.
Yes. What about x4?
3,
0
0.
x5?
0 1.
Okay, that's true. So this is
Plane.
so this is a plane. Because for x is equal to p. Now, can you check if this is a square? Wait a second. Okay. So, do you think that this could be a solution of the problem?
We can assign any values to x3 and x5, and then the values of the others x1, x2, and x4 will be determined.
Okay, but I'm just asking about this specific, which is drawn on the board. So could this be a solution? If you look carefully, this vector is this solution for s equal to t is equal to 0. So if we set s0, t0, this is what we get. Okay, so most probably this should be a solution of the equation which is initially offered over there at the top. Okay, which means that, for example, let's check this one. What is the first equation? The first equation is summation of all the x1, x2, x3, x4, and x5. This is equal to 3. Let's add these numbers. The first equation is confirmed, okay? Because this is x1 plus x2 plus x3 plus x4 plus x5. We get it correctly. The second equation, we can obtain the following. We get 2 times 1 plus, then we add up the next 3 numbers, plus 1 times minus 1, plus 1 times 0, plus 1 times 3, plus 2 times 0. This is equal to 4. This is the second equation. Is this confirmed? Let's check. 2 minus 1, 1, plus 3, 4. Okay, that's good. So the second equation is also good. The third equation, it says we have here
1 plus
1.
minus 1 times minus 1.
Yes, minus 1 times minus 1, and then?
Plus minus 1 times 0. That is
Yes.
0. Plus 1 times 3.
0.
0 equals 5.
Let's check. We have here 1 plus 1, 2 plus 3, 5. This is also confirmed. So it looks like you can check also the fourth equation, but it looks like this is a solution. Okay, so the question was, is this number an element of the solution space? We say yes. Okay. So it looks like the infinite number of solutions, it can also be a plane, okay, which is possible. Anyway, so the solution here, it is one-dimensional, one dim. A plane is two-dimensional solution. Okay, so why could the solution be 2 dimensions? Because it could be because of this. Initially, we said that we have 4 equations and 5 unknowns. But in fact, how many equations do we really have? If we look in here, we have just 3 equations because the last one is all zeros. So this is telling us nothing. So in this initial part, we said 4 equations, 5 unknowns. This is not true. We have 3 equations and 5 unknowns. Okay. So since we have 3 equations and 5 unknowns, this means that the solution, it is going to be a plane, a 2-dimensional plane. Okay. Because a unique solution, we could have a unique solution if we have 5 unknowns with 5 equations. Okay. But 5 unknowns with 3 equations, the best chance we have is this, a plane. Okay. So if we subtract the number of unknowns, if we subtract the number of equations from the number of unknowns, we get the dimension of the solution space. Okay. So we can say here that the solution space is empty if we have no solution, which would mean that the system of linear equations would be inconsistent. We would have the dimension of the solution space, dimension 0, if we have only one solution. We would have the dimension equal to 1 if you have an infinite number of solutions, if it would be a line, and so on. But this here, this is never an option, because so there are three possible options. A system has no solution, a system has one solution, or a system has an infinite number of solutions. So that's the 3 possibilities that one can get.
If equations are linear, because if they are grade 2nd, 3rd, it can be 2 or more solutions.
I agree with you, but we're trying to probably we're talking about linear systems of equations. Okay. So they are linear. You can. Okay, I'll just ask from you a few seconds because Professor Ilian is asking something from me. And okay, done. Okay, so now, so I think we clarified an important aspect here. The next element that we can discuss is the following. Let's assume, well, I think we had an option where this type of equation, there was a chance for it to be inconsistent. Pra nu të ndodhë që ne kemi ecuacion tek I cili nuk ka zgjidhje fare. And this type of equation, this is called non-homogeneous. This is non-homogeneous. Now, the terminology of homogeneous and non-homogeneous, you can see it also in differential equations. And hoping that probably one day when you see differential equations and you might remember something, I can give an example where this term appears in an equivalent form, okay, in a similar form. So we can have a differential equation that can look like this: the second derivative of y with respect to x plus 3 times the first derivative of y with respect to x again plus y. This is equal to 3x. Okay. Similarly, we can have the following: the second derivative of y with respect to x plus 3 derivative of y with respect to x plus y. This is equal to 0. Now, here we have two different equations that are differential equations. This one is called homogeneous differential equation. Okay, homogeneous. This one is called non-homogeneous. Now, you can see that if on the right side we have a 0, this makes it homogeneous. If on the right side is a non-zero, this is not homogeneous. So, if this is non-homogeneous equation, system of linear equations, what is the homogeneous part? The homogeneous equation, which would be similar to this, would be this one. Ax is equal to 0. So this is homogeneous. Now, I can ask you the following question. So, what do you think about this system? Is it possible, is it ever possible that this one, can this be inconsistent? This is the question. Can this system what do you think? To be inconsistent, this means to have no solution. Is it possible that this equation has no solution at all?
No.
No.
It has a unique solution.
What is the solution?
X is 0 over a.
You are
Infinitive, because
in fact, this is one solution. So this is a solution, which means that to be consistent, means that there is no solution at all. This is a very good option to be one of the possible solutions. So this can never be consistent because we can have equation 3x plus 2y plus z x minus y minus z 3x plus 5y minus z. This is equal to 0. I'm looking to myself twice. I guess someone of you has to help. And I think I can do it manually. Okay, one of you has the microphone and the speakers on, and the microphone on, of course. So this is what is this system of linear equations? This is a homogeneous system of equations. Okay, why? Because we can write this one as ax is equal to 0. Okay. So the b vector that we observe here, in this case, b is equal to 0, 0, 0. So what is one trivial solution? The trivial solution of this system is the following: x, y, and z. This is equal to 0, 0, 0. Okay. So this is the trivial solution. Okay, now regarding this, so it looks like this can sometimes be inconsistent, but this never. Okay, so we say here never. And then we have also something something more that we can add to this discussion of the solutions, and this is the following: the general solution. So whether this is homogeneous or non-homogeneous, they are two different equations. Let's call this one equation, the first one, the second set. And here, we can say that the general solution of ax equal to b, okay, includes the solution of ax equal to 0. Okay, so this is an essential. So this is a theorem actually, which states that the general solution of ax is equal to b. It includes the solution of ax is equal to 0. Now the thing is that the solution of ax equal to 0, the solution of this system, this is called the null space of A. So if we have a matrix A, or any matrix A, which can constitute or which can carry the coefficients of some unknown variables, A, or any matrix A, the solution of AX equal to 0
0 is the vector. 0.
is called, it's called the null space. So the null space or null space of A. Or similarly, this can be called also the kernel of A. So here we are starting to learn a few terms on linear algebra. So now let's throw out some numbers. Let's pick up an A, a coefficient matrix A, which what size would you like to have it? How many rows, how many columns? A like what? Say a couple of numbers.
4 by 3.
4 by 3, okay. If it is 4 by 3, a coefficient matrix, which is 4 by 3, how many unknowns can this have?
3.
3. Because if we multiply this A with a vector which is x 3 by 1, this would be equal to what? This would be equal to
A matrix 4 by 1.
exactly 4 by 1. So yes, this is how. But so this is the matrix A 4 by 3, and but when if B is equal to 0, 0, 0, 0, then the x because X is a solution. So X is the null space of A. But now, as we're discussing these, we looked at, so you know, when we discussed together in this class regarding the lines and planes, we used to ask such a question. We say that we find a line, and the first question that comes to our mind is that, does this line include the zero? Does this line pass through the origin? We can also ask this question. We found a solution which looks like a plane, which can extend in three-dimensional space, and again, we can ask the same question. Does this plane pass through the origin? Or yeah, this is the right answer. So now let's look at this x. So I'm just doing this as a reminder. Okay, so the solution, it could look like this: P plus TV. Okay. Or this was also one solution, which could be P plus TV plus SW. Okay, so these are possible solutions which belong to this category here. Now, I'm asking this: does this X include the origin? Does the null space of A include the origin?
Yes, because that's zeros.
What do you think?
I think yes, because it includes zeros.
Can you say it again?
I think yes, because it includes zero.
You are right. Does the null of A include the zero? The answer is yes. Why is yes? Because we know that if we multiply any coefficient matrix with zero, we'll get a zero. So let's not forget that the answer is zero. So this is correct. The null space of A, it always passes through the origin. Okay, and what does it mean for a vector or a plane to pass through the origin? Let's look at these equations. To pass through the origin, this means that we don't have this P. Okay? To make a line pass through the origin, we can simply write x is equal to TV. And since t can be zero, this passes through the origin. At the same time, a completely different solution, which is a plane now, which is TV plus radio plus SW. This one, since we have stripped out this, taken away the speed, we say that they pass through the origin. Similarly, null space of A, it also passes through the origin. Okay, so I think we try to make this as much clear as possible. So here we give an example of a system where the solution is 0, 0, 0 vector. So we take this away. And whenever the solution is equal to 0, we call it the trivial solution. We have a theorem which we can describe what we stated in a more elegant way, which reports that so let A be an M by N matrix, and B is a member of the RM. Okay, so A is an M by M matrix. B is element of Rm, which means that there are m different numbers that can construct the vector B, and Ax is equal to B is consistent. What this means that it has a solution. Okay, so apparently this has a solution. We know also that Ax is equal to 0 has also a solution, and but this one, since this one includes the solution of Ax is equal to 0, there is a chance that the dimension of this one, not dimension, but this is a little more general than Ax is equal to 0. Let's see what we say. Now, suppose that B is any solution of Ax is equal to B. Okay, so let's suppose that B is any solution of Ax equal to B, then the set of all solutions of Ax is equal to B consists of P plus Z. So P is any solution of Ax is equal to B, and the complete solution of Ax plus B consists of P plus Z, where Z is a vector in the null space of A. Okay? So apparently, any vector Z which is in the null space of A, we add any solution of Ax plus B, and this would be the solution. So mathematically, we can report it like this: X such that Ax is equal to B, okay, is equal to P plus Z, so where P and Z, they are both vectors, where Z is an element of the null space of A. Okay, so this is how we can read it. X, which is a solution of this, is equal to P plus Z, where Z is an element of the null space of A. Well, let's see another example. So let's try to find, let's assume.
Professor, how about we multiply A with P plus Z to get B?
I don't know.
Because P plus A multiplied with P plus Z, which equals B.
So
B, because P plus Z, it's included in the null space of A.
yes, I don't know.
And then we multiply again A with x minus P to get B. B minus
You see
equal 0. X minus P to get 0.
To get 0.
Yes.
I don't know. Let's see. 8 times X is a solution of X equal to B. So 8 times X plus 8 times is this. This is equal to now 8 times X. What was this?
0. That is 0.
You are right. 8 times X
B
is B. So here we
equals B. In the other multiplication,
yes.
we have AX, which is B,
Yes.
And 8b, which is b. b minus b will give us 0.
Let's check this carefully. Let's see what we get. A times
b.
But wait a second. Yes. Solution.
Yes.
Right.
Minus b.
What is A times B?
b again.
This is B again. That's right. We get what?
0.
Okay, yes. So from here, we confirm that this statement,
Stella, micrófono.
okay. So today we discussed a system of linear equations. We discussed the possible number of solutions. We discussed the reduced row echelon forms, okay, which was a very well-structured procedure, which we need to simplify the given set of equations, okay. We solved a couple of examples. The third one, we did not follow all the steps one by one, but our intention was to see how we get the equation of a plane. And these linear systems that we discussed, we call those linear systems with free variables, okay? Why do we have free variables? We have free variables because the number of unknowns, so actually, if A is m by n, what is the number of equations? We have m equations. What is the number of variables? M unknown variables. So if this is the case, what do we say? We say that probably the dimension of the solution, not probably, now when we say probably, if we have m equations given initially, it does not mean that effectively we have m equations. Those equations, they could be linearly dependent with respect to each other. We solved an example where we thought we had 4 equations, but as we're reducing it to a row-reduced echelon form, we noticed that we had actually less equations, because 1 or 2 equations that can be redundant, but assuming that if these equations are linearly independent, and they are equal to n, and if we have n unknowns, the dimension of the solution, okay, it's going to be equal, or actually let's think larger or equal to n minus n. Okay, we're going to see this one in more details as in the future weeks, but this is intuitive. That's why we are writing this here. Let's see, for example, what did we have as an example in the previous session? We had the following. We had 5 unknowns, right? We had 5 unknowns. We had 4 equations. And what did we find for the dimension of x? We found that the dimension of x was equal to 2. Dimension of x was equal to 2, which is larger or equal than n minus m. Let's check if this is true. Is it 2 is larger or equal? N was 5 minus 4, 1. That's true. This is correct. Now, why is dimension 2? Because we started with 4 equations, but we had only 3 linearly independent equations. So that's why the dimension of the solution space, it ended up to be 2. But why did we say this way? So you can read for any matrix, coefficient matrix A, m by n, which means that if it is m by n, we have m equations, we have n unknowns, then the dimension of the solution space. Why do we call this the dimension of the solution space? Because the solution is x, është e panjohura. Çdo ekuacion ku kemi një panjohur, pse quhet ekuacion? Se ka diçka që duhet me gjetë. Dhe bie këtu kemi, so we get here ax is equal to b. So this can be a line, this could be a point. no dimension. It could be a line, one dimension. It could be a plane, two dimension. It can be even more than that. So we call it dimension of x. It's anything like equal or larger than these relationships. Okay. So this is, we talked about the solution sets. We talked about the homogeneous systems, and now null space. What was null space? Ax is equal to 0. That was it. Then, other than this, I think we've covered the null space. We had a very good comment from you. I guess this will be more or less what we want to cover. So, with these topics that we just talked here, this is all the chapter 2. So next time, next session together, we are going to start chapter 3 from the book, which is about matrix inversions and matrix determinants. But before we go there, let's try to identify the null space of covering an example. Okay, so this is the matrix A, and we need to find the null space of A. But how is the null space MA? This is the question mark for us. So how is this defined? This is defined for x, which is equal to x such that ax is equal to 0. So ax is equal to 0 is the following. This is, what is the augmented matrix? We get here 1, 0, 1, minus 1, 2, 1, 0, minus 1, 1. And if we augment it with what? With the 0 answer, okay? So what do we need to do from here on? We need to calculate the reduced row echelon form. This is what we need to figure out, okay? And as we are working with this augmented matrix, so let me write this here. This is the augmented matrix. What operations are we going to do here? Will the operations, I believe, they are going to be something like this. Rj star will be equal to Rj plus lambda or minus lambda Ri. Okay, something. And as we do these operations, these zeros will always remain as zeros, right? Would you agree on that?
Yes.
Yes, okay, which means that, thanks Rugi. So this means that we can work with this one by even disregarding these completely. Okay, so we can leave it like this and we can work to obtain the reduced row echelon form. Then we move on. We say, what is the leading term is this one. Next step, we want to make zeros here. This 0 is already for us. Then what do we do for the third row? We see that R3 star, this is equal to R3 minus
the first row.
Thank you, that is true. So we go like this. This is 0, 2, minus 1. Here we get the following, 1 minus 1, 0, 1 minus minus 1, minus 2, 1 minus 0, 1. Okay, and then we move again. How can we do now? We can divide this number by 2, because we need the leading term to be equal to 1. So since we want it that way, we can move here and we can assume that we are going to do row 2 divided by 2. 1 minus 1, 0, 0, 1, 0.5. And this is 0 minus 2, 1. The next step is, actually let's do it here. The next step is So we have 1 here, we are happy. This is also 1. How can we make this 0? This is going to be row 3 star would be equal to row 3
plus double row 2.
That's correct. Plus 2 times R1. So this is what we have here, and then here we have the following. We get 1 minus 1, 0, 0, 1 minus 0.5, and here let's see what we get. We have, this is 0. We have here minus 2 plus 2. This is 0, and here we have 1 minus 1. We get another 0. Okay. Then, so we had 3 unknowns, right? We ended up with 2 equations. It looks like the solution is going to be at least a line. Probably you might already have figured this out. Now, how can we reduce this any further? I think we can use this element here to make this 0. Because all the leading ones should have only zeros above and below. So to do this, we use this second row as a pivot. Yes, as a reference of pivot. Then we see that row 1 star, this would be equal to row 1, then what?
Plus row 2.
Exactly, plus row 2. And then we come this way. We get the following. We have here, let's disregard, let's take this out, okay? Because it's offering nothing, no information. This is 0, 1, minus 0.5. And here we just add these two together. If we add these two together, we get 0 plus 1, 1. 1 minus 1, 0. And this is minus 0.5. Okay? So, this is we cannot simplify this any further because these elements, it's all 0 below and above. So what equations do we, how can we read these equations? Let's assume this is x, y, z. And we have, what are the leading terms? What are the leading variables?
X and Y.
That's true, x and y. Which one are non-leading or free terms?
Z.
Yes. So here we can see that z is equal to s. Z is equal to s, and then we try to write the following equation. We said x minus 0.5 z, this is 0. Then we have y minus 0.5 z is also equal to 0. So z, we have assigned this also as s. Okay, let's write here as s. And z itself is also equal to s, sorry. Then we need to write what is x, y, and z. X, y, and z is equal to, since we have one free variable, we can denote it like this. So what is x? We get 0 here and 0.5. Okay? What is y? Y is 0.
0.5.
That's true. What about z?
0, 1.
Okay, so it looks like the null space here is equal to s times v. So
It is a line.
it's a line. Does it pass through the origin?
Yes.
Yes, because it is 0, the first part.
That's true. So this one is 0. So this is like this. This is always like this. Okay. So then, what is the null space of A? Null space of A is the equation of this line. We can say that the null space of A is such that x is equal to s v, which means also that x equal to 1, 1, 2 is the solution of ax is equal to 0. Why? Because this is for s equal to 2, right? But This is the n of A. Do you have any question? So we are done with chapter 2. Of course, we're going to cover some other examples in the seminar sessions, but I strongly suggest you or recommend you to go over all the activities in chapter 2 and to solve those examples because you'll find them very useful. Okay, so again, I can ask one final time. So I guess if you have no more questions, we can stop this session. But I want to ask actually, are we going too fast or too slow? Or slow or normal? How would you?
A bit fast.
You think it's a bit fast?
Yes.
What about the others?
If we could go more slowly.
Okay. Okay. Yeah. Okay. So, but don't. So we're done with chapter 2 in theory, but we're going to have, of course, a few more examples, problem sessions. Okay. If you have no more questions, then I think we can. I want to thank you for your attention, and see you next session.
Thank you.
Okay, thank you. Goodbye.
Bye.
Goodbye.
Thank you. Goodbye.